So welcome back, and I do hope you and your family are keeping well. Right, we've had a look at energy transfers, and we've talked about the types of energy, the places we see energy rear its head, as it were, kinetic, potential, etc. And we've talked about how we can transfer energy from one place to another. So I've just picked the simplest of demonstrations here. I'm just going to literally light a little light bulb, and as a bit of a reminder, to say to you, okay, what are the energy transfers here? So I hope you remember, maybe pause the video and think what the energy transfers are. So I'll go through it anyway. Inside the batteries, we've got potential energy in the form of chemical energy. So it's sitting in the batteries waiting to do something. Should we just call that chemical energy? In the wires, we've got electrical energy. And finally, that transfers into heat and light in the lamp. But it's not that I wanted to talk about today. That's a little bit simplistic. What I wanted to do was to show a better way of showing the energy transfers in any system, and particularly a way of really cleverly showing what percentage, what fraction of the energy in the light bulb turns into heat and what fraction turns into light. And so what we're going to be looking at is energy transfer diagrams, and particularly the Sankey diagram, and then I'll do a little bit of a talk about what we understand by the term efficiency. Okay, so now let's have a look at a better way of demonstrating energy transfers, and something we call the Sankey diagram. And then I'm going to have a look quickly at how that shows us what's meant by efficiency. So if you were to draw the energy transfer in a light bulb, you might do something like this in the light bulb. Okay, so it's electrical. So we'll just do the bulb. It's electrical converting to heat plus light. Okay, and that explains pretty well what happens in the bulb. So the bulb kind of sits here as the device that converts electrical energy into heat and light. But there's a slightly better way of doing this. Wouldn't it be better to sort of get rid of the plus sign and say that electrical energy converts to the light that we want plus some heat that we don't want. And this is a bit annoying about filament light bulbs, is they use a really hot wire. I think Edison was one of the inventors of these sorts of things, and you get the wire hotter and hotter and hotter, and it gives out light, but it also wastes a lot of your battery's energy giving out heat. And this projector I use, you can hear it humming in the background, actually has to have a cooling fan on it, because the lamp in here is so bright and so hot it wastes a lot of energy as heat. It's very inefficient, very inefficient. In other words, a lot of the energy that we get out is wasted. We don't get a large fraction out that we want. We actually get a small amount out as light and a large amount out as heat. And those processes, aren't good for energy transfer. We try to make systems that are more energy efficient. So I'd like to analyse this second diagram that I've drawn here, and they're good diagrams to understand the energy transfers in systems, but I'd like to draw it in a slightly better way to give some idea of how these two split up. How much light are we getting out compared to the heat? So we're going to look at the Sankey diagram. Right, so here goes for a Sankey diagram. Interesting name, Sankey. Let me just write it down. Okay, interesting because down the road from where we are here, we've got GKN Sankey, and I just wonder whether it's the same person who did this sort of work. I think Sankey was involved in making steam engines more efficient, but perhaps Google that. And I do remember seeing an original Sankey diagram, and it was a complicated mass of arrows going around in all sorts of directions. We're going to use it at GCSE in a slightly more simple way. Okay, so this is what Sankey basically did, and you'll see these a lot in exams. I'm going to change these arrows here to having some thickness, and the thickness is sort of representative of the amount of energy that we've got going into the system. Okay, so we'll make that line the electrical energy coming in to the lamp, and it's going to split up into heat and light, 2 arrows. So what I'll do is I'll have an arrow going off in this direction, and that's the energy that we want, the light, and this is the wasted energy that we never wanted in the first place. That's the heat. Okay. Now, there's some really, really important features of this diagram, and I want to make those really clear. Firstly, that's a much better diagram than that one, and certainly better than the first, because it says we've got this amount of energy coming in, and we're going to get a small amount of light and a large fraction as heat. But here's a really important feature of this type of diagram, that the width of this arrow must be equal to the width of these two pushed together. Okay? That's a really, really important idea. It's important because if you feed in an amount of energy, you can only get out the same amount. You can't get out more. So we're looking there at a bit of physics called the law of conservation of energy. Okay? Try and understand what the word conservation means here. It's slightly different from how you might use it in the English language normally. The law of conservation says, of conservation of energy that is, you can't create or destroy energy. You can only change it from one type to another type, and you'll always get the same amount of energy out in total that you fed in. Okay? Well, that's fair enough, because we fed in this width of arrow, and if I added that width to that width, it would be the same. So I'm not disobeying the law of conservation of energy here. If you have to draw these, be really careful that you don't make these 2 or 3 wider than that one. There's another little trick that's worth mentioning as well. Which way do the arrows point? Well, they always go from left to right at GCSE. And which way do these point? Okay, who knows? They can be in all sorts of different directions. You usually draw the energy that's useful this way and the energy that's wasted being dumped downwards. But in an exam, I've seen it in all sorts of different ways. I've seen the energy we want that's useful coming this way and the wasted going up into the atmosphere, an arrow pointing upwards. So you can't learn the directions here, just draw the arrows and label them correctly. And this one we'll call useful, and this one we'll call waste energy. And I'll just end this little segment by saying, look at the width of that arrow. This is really inefficient. We're wasting a very large fraction of what we actually put in. So the light bulb with a filament is not a particularly good light bulb for giving out light. What it mainly does is heat the room up. So as ever, pause the video and think about what I've said, because it's all happening very rapidly, isn't it? No chance for you guys to interact with me and ask questions and things like that. So you need to pause each bit and go, yeah, I've got that, so I can take you on to the next stage. Do you remember energy is measured in joules? So let's feed in here 200 joules of energy. Okay, so it's typical FJ, it's just make up a number, 200 joules of electrical energy coming from the battery into the wires, getting into the lamp, and the lamp is splitting it, shall we say, into 120 joules of wasted heat energy. Now, if you've listened to what I've said about conservation of energy, you immediately know what this has to be. If we feed in 200, we can't create or destroy energy, we can only transfer it from one form to another. So 200 in is, push those arrows together, 200 out. So if we have 120 joules here, we must have 80 joules of light energy. So we've used a Sankey diagram to show the energy splits. Now, the last little bit I'd like to look at on this is efficiency. And I usually find people seem to find this really, really difficult, but it isn't. If something is efficient, listen carefully, okay, if something's efficient, it wastes a small fraction of what you feed in, okay? So let's do it for this example. This is inefficient because it wastes a large fraction of what you put in, okay? It's not good to teach you the wrong thing, but I'm going to do it anyway. Okay, I'll tell you what efficiency isn't. Efficiency isn't it wastes a large amount of energy. Because this could be millions of joules, and this could be a million joules. So it's a very large amount of energy, but so's the top one if that was a million joules. So don't talk about wasting a large amount. No. Efficiency is about if it's an efficient system, it wastes a small fraction of what you feed in. And this is inefficient, so it wastes a large fraction, percentage. It wastes a large percentage of what you put in. Okay? Now, if you look at this one, what I'd like you to think about is if we put in one amount of energy, how much do we get out on this side? If we were to put in 1 joule. That's sort of how efficiency does things. But I'll show you how we calculate efficiency. Okay, so the efficiency of any system is the useful energy out divided by the total energy you put in. That's pretty obvious, isn't it? The efficiency, how good it is what you get out compared to what you put in. What you get out compared to what you put in. Okay? I always describe this as, you guys kind of understand efficiency. It's like asking your parents, they come up to you and they say, can you clean the car? Yeah? Can you clean the car? And you go, yeah, sure. What do I get out of it? Okay? And if your mum and dad say, we'll give you 10 pence, you'll go, your brain goes, that's not very efficient. I'm not getting a lot out compared to the effort I have to put in. Okay, so our economic efficiency. Whereas if they say, okay, you clean the car and we'll give you £10 because that's what it costs in town to do, you'll go, well, that might be worth it. Yeah, I get a reasonable out from the effort that I put in. Okay, so if you look at this one, it's really quite an easy calculation. The efficiency here, yeah, is what you get out, 80 divided by what you put in, 200. Okay, and that's going to come out as 0.4. Okay, so you bash away with your noughts there, and 8 divided by 2 is 4. Got an extra 0 underneath here, so 0.4. Now here's the really clever bit. Okay, this is measured in joules. This is measured in joules. Okay, so joules divided by joules. I'm really I don't like saying the word cancelled. They don't actually cancel. It becomes 1 divided by 1 with numbers. But if this is in joules and you divide by joules, the joules go, and so that's the efficiency. Okay, it doesn't have any units. It's just a number, 0.4. Okay, and that's good enough for exams. Yeah, that's good enough for exams. But if you look at this diagram, lots of people want to go 200 in, 80 useful out, 100 in, 40 useful out, so it's 40% efficient. So if you were to times this by 100, yeah, you would get 40% efficient. Now the 0.4 is absolutely fine for exams, so if you use that number, no problem at all. Final thing I wanted to say on this is, you've got to think a bit carefully, guys, because I've worked out the efficiency here, but this is an equation. So what would happen if they gave you the efficiency and they asked you for the useful out? Efficiencies are always less than 1. Okay? So if they gave you the efficiency and they asked for the useful out, total in multiplies on this side, so the total fed in multiplied by the efficiency will be the useful out. And if they asked you how much you fed in, total in will be useful out divided by efficiency. So you do have to be able to rearrange equations. Anyway, that was a fairly quick lesson on energy transfers, simple diagrams, the Sankey diagram, putting energy values onto the Sankey diagram, and finally the efficiency equation. This stuff comes up a lot at GCSE, so have a good look at it, and I wish you luck, and I'll see you next time.